In this second video, we'll look at how we can use valence bond theory to describe the two types of bonding, the sigma bonding and the pi bonding. In this slide, you see a representation of the sigma bonding. Sigma bonding involves a direct head-on overlap or a head-to-head overlap. So for instance, if you look at the two 1s orbitals, each containing one electron, and allow the two orbitals to come together and overlap. The idea is that there'd be a high likelihood of finding a shared pair of electrons with opposite spin in the internuclear distance. This would provide a high electron density where there'd be a mutual attraction of each nuclei to the shared pair of electrons. In other words, the chemical bond. You can also see a representation of two Sp2 hybrid orbitals overlapping in a similar way. We'll describe momentarily the nature of an Sp2 hybrid orbital. So the key idea here is think of the sigma bond as involving a direct head-on overlap. If we now consider, for instance, the pi bonding, which is the second type of bonding, this always involves p orbitals. So here we have representations of boundary surface diagrams of two 2p orbitals. Each one contains one electron. You bring the 2p orbitals together, and now there'd be a side-by-side overlap. There'd be a side-by-side overlap resulting in a pair of electrons simultaneously existing both above and below the plane. If we think of electrons as only particles, it would be hard to reconcile this idea. So it's helpful to think of the electron as a wave, and there would be some wave electron density both above and below the plane. This results in the pi bond. Because there's this side-by-side overlap, both above and below the plane, pi bonds are normally considered to be the weaker of the two bonds. And so it's helpful to keep in mind that the bonding electron density, as I say, is found both above and below the plane where the nuclei are found. Now, to show how these two types of bonding are involved in putting molecules together, we will start with the simplest of molecules, and this is, of course, methane. Now, the representation shown on the right-hand side is a ball and stick showing the tetrahedral arrangement of the carbon-hydrogen bonds. Now, we know from experimental data that indeed methane and its corresponding atoms exist in this tetrahedral arrangement. The hydrogen-carbon-hydrogen bond has a bond angle of 109.5. Our bonding models have to be consistent with what we know to be experimentally true. Now, I'll come back to this slide in a minute, but I ask you to take a look at this diagram, which is found on the next page in the middle part of the page. And we're back to these energy level representations. And we see here a representation of carbon in ground state with its 1s2, 2s2, 2p2 electron configuration. Now, we know that the 2s orbitals and the 2p orbitals do not have the correct geometry to be able to result in a tetrahedral orientation. Also, remember that in our valence bond theory, it's each orbital bringing one electron. So as such, in ground state, carbon could only make two bonds. Now, the work of Linus Pauling in the 1930s helped move forward valence bond theory. He anticipated that when atoms engage in bonding, as the atoms come together, there is energy available, this sort of bonding energy, that allows the electrons to become somewhat excited. So if we look at carbon in an excited state, we'll bump up one of the electrons from a 2s orbital into a 2p orbital. Now we have four individual electrons, which could be involved in four bonds. Again, the orientation in space is not quite right. We know, of course, that the 2p orbitals exist perpendicular relative to one another. So there's something else that indeed happens. Linus Pauling did some fancy math, and he anticipated that what occurs with this extra energy that's available is that indeed four brand new orbitals are made from these original s and 2p orbitals. This process of forming brand new orbitals is called hybridization. And so as such, we'll take one s and three of the 2p's and form four brand new Sp3 hybrid orbitals. These hybrid orbitals would be of intermediate energy between the 2s and the 2p, but they would all be of the same energy. In other words, they'd be degenerate. And so I'll put 4 electrons, one each, into each of the sp3 hybrid orbitals. So this is what we would consider to be a hybridized state. Now it's helpful then to look back at this diagram where we see the original boundary surface diagrams of the 2s and the 3 2p orbitals. There's the hybridization forming the 4 brand new sp3 hybrid orbitals. And perhaps miraculously, these 4 sp3 hybrid orbitals have a geometry which collectively would make a tetrahedral. So now back to this original slide, what I'm trying to show on the right here is the 4 sp3 hybrid orbitals arranged in a tetrahedral geometry. So the tetrahedral arrangement of the 4 sp3 hybrid orbitals, and of course the bond angles between these sp3 hybrid orbitals would be 109.5. So our valence bond theory is now consistent with the experimental evidence that we have. Now I'm going to take you away from the slide for a minute. I'm going to take you to a website which represents something similar. So in this representation, we're starting with carbon in the excited state, but we still have the original atomic orbitals. And so what I'm able to do in this simulation is separate the orbitals. We can picture that there's one electron in each of the orbitals. So there's the 2s, there's the 2p y, there's the 2px, and the 2pz. Of course, these do not have the right orientation to be able to form a tetrahedral geometry. Linus Pauling, as I say, did the mathematics to see what would happen if you, in a sense, combine these 4 orbitals, in a sense, hybridize them. And as such, the simulation shows if we hybridize, that is, mathematically combine the function for those 4 different atomic orbitals, we end up with these 4 hybrid orbitals. You can see that their shape looks something like a mushroom, and their geometry indeed represents the tetrahedral orientation, which is necessary for an sp3 hybridized carbon. So now back to the slides. I'm just going to open this up and bring us back to where we were. Okay, and now moving forward, you can see a wedge and dash representation of the tetrahedral arrangement about a carbon in methane. And then we move to the boundary surface diagram of the 4 sp3 hybrid orbitals. Of course, we also have the hydrogen s orbitals. And now we would have the overlap of the hydrogen s orbitals, one each with each of the sp3 hybrid orbitals of carbon, finally forming the methane molecule on the right-hand side. And so we'd have 4 sigma bonds between the carbon and the hydrogens. So this is how we view bonding according to the valence bond theory. Now, valence bond theory would not be effective or helpful unless it could also explain the other kinds of bonding that exist, including the pi bonding. So let's take a look here. We have in teaching model number 4 an example or representation of formaldehyde. Now, carbon in formaldehyde is only making 3 sigma bonds. So let me show you how this works. So we have the initial ball and stick representation, and we have a sigma bond to a hydrogen, a sigma bond to another hydrogen, and then a sigma bond to an oxygen. This would be a trigonal planar orientation, and the bond angles, as determined experimentally, would be expected to be about 120 degrees. We will anticipate that instead of being therefore sp3 hybridized, the carbon in this case is what we call sp2 hybridized. And there will be 3 sp2 hybrid orbitals involved in making these 3 sigma bonds. And so this representation is shown on the right-hand side here. But I need to explain to you a little bit what we mean by sp2 hybrid orbitals. So looking further in the notes, we see these boundary surface diagrams. Once again, we're starting in a sense with the excited state carbon with its 2s and 1 electron in each of these 2p orbitals. In the hybridization, however, we'll only use these 3 orbitals. We'll form 3 brand new sp2 hybrid orbitals, and we will leave behind one of the other p orbitals, which will sit perpendicular to these sp2 hybrid orbitals. Now, I've indicated this as the 2pz. It could have been any one of the p orbitals that's left unhybridized. Now, how does this explain the bonding in formaldehyde? Well, carrying on, we see a wedge and dash representation of the formaldehyde molecule. And then we see carbon, which is sp2 hybridized, as well as we will see later, oxygen is also sp2 hybridized. Why oxygen adopts sp2 hybridization will be explained in a subsequent lesson. So carbon, with its 3 sp2 hybrid orbitals, and then its 1 p orbital. And remember, there is only 1 electron in this p orbital, although we have lobes both above and below the plane. Of course, each hydrogen is bringing 1 electron. Over here with oxygen, we have 3 sp2 hybrid orbitals and then 1 unhybridized p orbital. We allow these 2 atoms to overlap as well as the carbon to overlap with the hydrogens. And we end up forming this formaldehyde molecule. So for instance, we have the overlap of each of the carbon sp2 hybrid orbitals with an s orbital of hydrogen, forming 2 localized carbon-hydrogen sigma bonds. We also have the overlap of the carbon sp2 hybrid orbital and the oxygen sp2 hybrid orbital to form the localized carbon-oxygen sigma bond. Further, we have a localized carbon-carbon pi bond, which involves the side-by-side overlap of each of the p orbitals from carbon and oxygen. Now remember, there's only 1 pair of electron in this p orbital. The pair of electrons exists simultaneously both above and below the plane of our carbon-oxygen sigma bond. Finally, there are 2 lone pairs of electrons, and these would be an sp2 hybrid orbitals of our oxygen. Now, to help you see this further, I'm going to show you a diagram that's not in your notes, but I think will be helpful to picture what's happening. Now, this involves this ethene molecule. So instead of having an oxygen on the right-hand side, I have another carbon making bonds to 2 hydrogens. So starting with the left-hand side carbon, where the carbon is sp2 hybridized, that's in purple, we see the sigma bond between each of the hydrogens, and then we see the unhybridized p orbital. Now I'm going to bring this first carbon that's on the left to the second carbon on the right. And the first thing that we'll see is the head-to-head overlap forming the sigma bond between the 2 carbons involving their sp2 hybridized orbitals. If I bring the atoms closer, we also see the formation of a single pi bond both above and below the plane of our carbon sigma bond. And so you can perhaps get a sense from this simulation that the pi bond would be the weaker bond, and it's the pi bond that would be involved in the reactivity of this ethene molecule, the reactivity of our formaldehyde. So the pi bond will be the last to form in a sense, and the first to break, and then the sigma bond. So hopefully this simulation helps you see what's going on with the formation of formaldehyde.